Hi and welcome. This video is about a plugin we developed at the Laboratory for Timber Construction at EPFL. So the goal of this plugin called Manis is to enable a collaborative workflow for the design of timber plate structures connected by wood-wood connections. So in the example I will show today, we will see how the plugin allows the generation of the joint's 3D geometry, the fabrication files for CNC machining, the robot trajectories to automate the assembly, and finally the FEM model for the structural analysis. Our case study today will be the structure of the Annen headquarters. As you can see here on those four pictures, it is a doubly curved vault made of a series of interlocked timber panels. And in this video, we will apply our joinery solver to 9 boxes that are isolated from one arch of the project. So let's start right away. If I go here on my grasshopper canvas on the left, I will make first the structure appear. So here are all 9 boxes. So as you can see, we have here a little guy called Plate Model Builder, which will build a plate model, so assign new attributes to the geometry that we draw in Rhino. So we have our arch here. For now, we don't have any joinery, no added data that could be useful to us, but this is what Manis will provide in the next steps. So it is also important to specify an assembly sequence for the plate model builder, because what is important for us is to know the order of assembly of the different plates in order to compute a joint that will be compatible with the assembly. So here each plate is assigned an ID, 0 to 35, that represents its position in the assembly sequence. So you can see on the grasshopper canvas here that we have our modules of 4 plates each that are grouped with the hooks. So we have a module of 4 plates, 0, 1, 2, 3, which is the first red box here in Rhino. And then each box will be assembled with the previous ones during the assembly process. And so you can specify here the assembly sequence that you want or that you think is the best for your structure. And automatically, the plate model builder will compute the correct vector of insertion to insert the boxes into one another. So the plate model builder will also compute adjacency, so how the plates are connected. So you can see here we have a module called contact zones that will just compute all the zones, all the areas where the plates are touching each other. So if I disable this, you will see better. Here are all the areas. Some of those areas, we don't want them to be computed in the model because they will interfere in the assembly sequence if we will keep them. So we have also a parameter here called discard, where we can manually specify a few areas of contact that we don't want to be taken into account during the computing of the model. So here's our initial setup. Then we will generate the joints in that next part. And you see I have a lot here of different components, but a few of them are the same. So we'll start here by generating sunrise dovetail joints. So if I display the structure again, maybe more like this one, you will see the difference. Here, now we are creating what we call the Nejiri Arigata joint in Japanese, or sunrise dovetail joint in English. It's a very nice joint that is here automatically being computed between edgewise connections. So when the two plates here you see in Rhino, we have one coming at the edge of the top plate of this box. And so this type of joint can only be applied for that configuration of plates. So for the other plates, which are not on the edge as you see here, we need to compute another type of joint. And in that case, we will choose the true tenon joint, which is classical one. And here, since we have various configurations and sometimes we need the joints to be alternated, you see that we have several tenon components that will in fact just apply to some selections of plates. But in the end, what we will get is here all the joints together that are generated according to the parameters specified by us. So you see that we can change also the tenon number, the length, the width, the spacing, shift, and so on. So for all joints, they can be parameterized. Here I will not modify it because we are also more computationally intensive components after, so this will be for maybe another video. So now we have all the joints that are created, and we would like to check maybe the assembly sequence, for example. So for this, we can go directly to assembly here, where we can display, we'll just hide the rest so you can see better. So we can display here the assembly sequence for one of the modules. So let's take, for example, the first box. So I put module ID 0. Here I have my component called animate sequence. I will zoom correctly on Rhino, and normally we should see it up here. Yep, some lag, and you will see how the plates are connected. So I can rotate a bit the view. Here you see the two joints being inserted, and then we have the true tenon joint coming laterally in the two previous plates. And you see that the shape of the joint has been computed according to the assembly sequence, because the plate 3 and 4 here have an inclined tenon that is compatible with the position of the two previous plates. So this is for one box. And now we would like to display also maybe the assembly of the full arch, because we have a kind of two-step assembly sequence where we first assemble the boxes and then our module of 9 boxes. So I can go to the very end here of my module. So we have 9 modules of one box and one which represent the full assembly sequence. And so here you can display the assembly of the boxes. And so you see that when they come laterally, here we computed an insertion vector that is perpendicular to the plates. And so when it comes on top, we have a 90-degree tenon angle, while here it needs to be computed between two previous boxes. So all the joints are automatically computed with this plate model builder. So here we get the assembly sequence. So you saw here also that we have merged joints with plate components. So this guy is quite computationally intensive. He took approximately 10 seconds to compute all the joints. So in fact, what we do is that during the design process, we have the joints separated from the geometry, and only at the end we can merge the joint with the plates to get a single geometry for visualization purpose. So here's our end result in terms of geometry. Now, for example, we would like to display the CNC toolpath. To do so, first we will display all the plates in an array. So here you see them all together. So you can play a bit here with the different parameters to distribute the geometry as you want. So here it's easy because we have 36 plates, so it fits well in a 6x6 grid. Then here we have toolpath generator, which is also quite computationally intensive component depending on what you want to compute, because it needs to deal with offsets, but also with some notches. So you will see what I mean directly. So here we wanted to compute only plate 0. And let's zoom on plate 0 and its toolpath. So you see that we automatically generated the offsets, but also the small lines that you see here to generate notches that are required for the insertion of the tenons. And we can also display them by, again, running the merge joints with plates component, which is essentially doing Boolean operations. So here you see the plate in its final stage, with all the corners being rounded in order to be able to insert the pieces into one another. If we wouldn't do so, we would have here a rounded corner inside of the joints, and it wouldn't be possible to insert them together. So the toolpath that we generate is taking this into account. And you can also specify a dog bone notch if you want, where the notches are going to appear in the corners. So here you can generate this for the 36 different plates, and then you can simply send it or convert it to a G code using a MATCAM, AlphaCam, or other processor for the toolpath. So for the assembly, we can also go to a robotic assembly. So this is one of the other tasks that Manis can perform. So we will again move our model of plates into different position. So we will stack a few plates on top of each other, and we will rotate the model like this. And here for the assembly with the robot, we will just select the first module, because we don't want to assemble the full structure with a robot, but just to automate the assembly of one module. So here we can isolate those little guys here and generate a robotic trajectory. So maybe I can first show you our robot. It will be better. So here you see the robot we have at Cibois. It's also provided in the example file, but you can also use your own, of course. And here we have the robot trajectory. So the robot plugin we use is a plugin named simply Robots. It's developed at the Bartlett by Vicente Soler. And so it's a very handy plugin for visualizing and generating those robot trajectories. And here I decided how I wanted to generate the trajectory more manually. So we'll have here a list of planes that is automatically computed. It's a simple pick and place operation, but where we also have the last segment, which is the insertion segment, which is varying in function of the shape of the joint. So here in the end, you can also simulate the plate moving with the robot together. So we have a plate simulation component here. So let's see if I can make it work. So you see our initial model and our final model, and here the list of plates, and here the robot grabs the first plate, inserts it, and so on. Our tool here is not really adapted to the size of the plates, but you get the principle. You can adapt, of course, the end effector of the robot. The last part of the framework is the FEM analysis. So we wanted to provide designers with a sense of how the structure behaves. So I collaborated with my colleague Ariane Zairat, who developed a macro modeling technique for timber plate structures. And we developed together this small component that relies on Compass framework and Abacus software. So Compass is an open source platform developed by the NCCR Digital Fabrication. It fosters also the collaboration between designers, architects, engineers, and so on. While Abacus is a private software developed by Dassault that enables the analysis of structures. And so Compass integrates a module that allows to run Abacus on complex geometries. And so we developed this little guy here to make the connection with Manis. So just quickly to show you, here we have the input mesh. So it's just the midplane of each plate that will be connected with the other plates by those small lines that represent all the connections in the structure. And so we have a kind of simplified version of the structure that we will be able to set as input for the FEM analysis. And so we also define, of course, some support condition and some loads that you can see here in Rhino. So all of these are generated automatically in Grasshopper, but you can, of course, select your own kind of inputs. And then we ran the analysis with the different parameters that we set up in Grasshopper. So you have here the elasticity, Poisson coefficient, density, thickness of the plate, width, height of the connections, and the uniform load that is applied on top of the structure. The FEM analysis runs in more or less 1 minute because Abacus is quite an intensive program. But here we have already the result computed for you. So we can display the deformation of the structure, for example. Let's compare it maybe to the initial mesh. You see the difference for that plate. Typically, it's exaggerated, of course. It's 100 times exaggerated. And you see here how the different stresses are displayed on top of the structure. So this concludes here our little tour of what Manis can do. We will try to provide maybe other and more in-depth explanations in another video. Thank you for your attention and see you in another video. Bye.